What we have here is the moon going around the Earth in a very elliptical orbit. Turns out that all orbits are elliptical, not circular. Johannes Kepler looked into that and he came up with 3 laws of planetary motion. Let's talk about that. His 3 laws, and keep in mind that in physics, laws just mean that we have an equation for it. So he took Tycho Brahe's data. Tycho Brahe was the Danish royal astronomer for his career, and he took readings on stars and planets for about 20 years. He had reams of data. Johannes Kepler was hired to analyze that data. So he used the mathematical tools to summarize the data in equations. So what you need to keep in mind is that in physics, when we say there is a law for something, that just means that we have an equation that we think works reasonably well. Took him about 10 years to come up with his first 2 laws, and then about another 10 years to come up with his 3rd law. And this is because he didn't have any computers to do the calculations. He had to do everything by hand without a calculator. So his first law that he came up with was the law of orbits. And this is, as I started by showing with that simulation there, the fact that orbits are not circular, they are elliptical. And this focuses on the whole orbit. It compares a satellite's entire orbit to a circle. So I have here one orbit, and let's say that we have a planet. Here's a planet. Could be a planet or going around a star, or a moon going around a planet, or a satellite going around, or an artificial satellite going around. It doesn't matter. What matters is we have one body orbiting another body, and we've already talked about center of mass. So what's actually happening is both of these guys are orbiting their center of mass, but if one guy is much, much bigger than the other guy, we basically just say the planet goes around the sun, even though the planet and the sun are both orbiting their center of mass. And up until Johannes Kepler, all the scientists and anybody who looked at the stars and anybody who thought about this said they're going in circles, where you have the radius at this point and the radius at that point and the radius at that point. They're all the same radius. And Kepler found out, actually, no, it's not that way. They're ellipses. And the way you draw an ellipse is you get that same string, but you pin it at 2 points, and you drag your pencil, or in this case chalk, around, and it will make an ellipse, where when you add up the 2 distances, that is constant, as opposed to we just have them overlapping because they're pinned at 1 point. And the sun is at one focal point, and there is nothing at the other focal point. Fortunately for us on planet Earth, these 2 points are very, very close together. So our orbit is almost a circle. And because it's almost a circle, until you take really detailed, careful measurements, you're going to look at that and say, yeah, that's a circle. Because if I took this guy and I put this second point right next to the sun, or possibly inside the sun, it's going to look, if you zoom out, like a circle. There's going to be a point where the planet is closest. That is called the perihelion. Near the sun, helion being sun. Now, when we have a satellite or the moon going around the Earth, it's not perihelion, it's perigee. And the maximum is aphelion or apogee. So, perigee and apogee. And that just means near and far. The eccentricity is how oval-shaped the orbit is, or in the orbit or the ellipse. This goes for any ellipse, not just orbits, and it's a number that we summarize with the letter E. This is not e of exponentials 2.71728. No, this e is eccentricity e. And the equation for that is R max minus R min divided by R max plus R min. Now, if these two guys are the same, meaning we have a circle, that's a 0 up here, and the eccentricity is 0. If, however, these two guys get too different, then we get a smushed flat oval, and you get something like a comet's orbit. Think about Halley's Comet, which comes in close to the sun, and then it goes way far out from the sun, and it takes a long time to come back. And this is because it slows down out here, and it spends a lot of time out here far away from the sun, and then as it comes in, it goes much faster. And you saw that in the simulation here. You can watch it getting slower as it gets farther away, and then it speeds up as it gets closer. Kind of looks like a slingshot. And we'll talk about that for Kepler's law number 2. He published law 1 and law 2 together. That's the law of areas. The verbal part of that is, remember, law means we have an equation for this. The equation for law 1, the law of orbits, is the eccentricity equation. Law 2, law of areas, satellites sweep out equal areas in equal time. What this does is this compares one part of a satellite's orbit to another part of the same orbit. So let's take a look here, and we're going to compare one part of the orbit to another part of the orbit. So what this is saying is, if we take that window and our planet goes from here to here, and let's say this takes, 10 days. If we come over here and we take that same 10 days, we're going to have a wedge that's shorter and fatter, but the areas are going to be the same. So area 1 and area 2, so here's area 2 and here's area 1, they're going to be the same area. Now, if you make this small enough, this wedge, this pi wedge, is basically going to be a triangle. And we can say, hey, area of a triangle is 1/2 base times height. Well, the base is this arc length, and the height is the radius. Now, over a short enough time period, now this has to be a short time period, the radius from here to here is going to be roughly constant. We're doing approximations here. Remember, he doesn't have a calculator, he doesn't have a computer, he probably didn't even have pencils. I think he was using quills. Because this is the 1600s. This is the early 1600s. So this is, he publishes these guys in 1609, and he publishes law of periods in 1618. So he's spending, 1600 to about 1620 doing this. Not the best computing power available. So 1/2, and the base is arc length. Arc length is r theta. And then the height is the radius. You should know from math class, this length right here is r theta, where this is theta. And then we're going to have the same thing over here, where this is r theta, and then this is its own radius. So area 1, we're going to have radius 1, theta 1, and then that's radius 1. And then the same thing down here. And what's necessary is that these guys be in equal time. So we're dividing by a time here, and we're dividing by a time here. So we come over here, divide by time, and we divide by time. Let's rearrange those equations and see what we get. Now, I've grouped it on purpose because over that short time period, the radius doesn't change. It's the angle that we're moving through. And you should remember from circular motion, theta over time is the angular speed. So this guy can be rewritten as 1/2 R1 squared omega 1. And this guy is 1/2 R2 squared omega 2. And what we have here is something that we've already talked about. It's called angular momentum. So let's play with this equation just a little bit more to see that. So on this equation, or in this equation, we have what are we missing here to get angular momentum? Well, what we need to do is multiply by a mass here. So area 1 over time is going to be equal to 1/2 R1 squared omega 1. And if we multiply by the mass of that satellite, well, we can multiply by the mass of that satellite. And remember, this is area, not acceleration. And let's multiply both sides by 2. Move that guy over. And what we have is the rotational inertia of that satellite. It's just a little tiny point particle. I mean, look at the size. The size of our planet compared to the size of the orbit is very, very small. So this is essentially a point particle. This is I. This is omega. This is angular momentum. I1. This is omega. This is angular momentum. And what Kepler found is A1 over time equals A2 over that same amount of time. As long as the time is the same, the areas will be the same. Well, if we multiply both sides by 2, like I did up there, and then we multiply both sides by the mass of the planet, I'm doing the same thing to both sides. I'm just playing with algebra here. What I found is, based on up here, this is I1 omega 1 L1, and I can do the same exact thing for 2. So this guy is angular momentum of the planet at point 1, and this guy is angular momentum of the planet at point 2. What Kepler discovered, and he didn't name it this way, it took a while for physicists to come up with conservation of momentum and conservation of angular momentum. So what we have here is Kepler found conservation of angular momentum. He didn't use the word momentum. He certainly didn't think of it this way, but that's what he found. The one who found that and used it in his laws was Newton, but that was 70 to 80 years later. So the upshot of Kepler's law of areas, and he phrased it as areas in equal time, is conservation of angular momentum. His third law, the law of periods, took him another almost 10 years to figure out. Again, keep in mind, he's doing this without electricity, so he couldn't, if he was going to stay up late at night and do these calculations, he was doing it by candlelight, and he didn't have a calculator. The ratio of the cubes of the average orbital radii is equal to the ratio of the squares of the periods for any pair of satellites orbiting the same body. All right, that's a mouthful. It's a lot easier just to write the equation. So we've got planet 1 and planet 2. If we cube the average radius, so you take the R min and the R max and you average the R min and the R max that I referenced earlier, and I have a diagram for that back there. If you cube that guy and you cube this guy and you divide them, you're going to get the same result if you take the periods for each of those guys and you square them. Now, we can take a look at, we can do a relatively simple calculation. Let's say that planet 2 is the Earth, and let's say that planet 1 is Jupiter. So we'll turn this guy into Jupiter and that guy into Jupiter, and we'll turn this guy into Earth and this guy into Earth. And we have a very nice and geocentric way of measuring things at the astronomical level. It's called everything relative to Earth. So all the other planets in our system, we measure their periods. How long does it take them to go around the sun relative to one Earth year? So for the Earth, the period of the Earth is one Earth year. Well, we do the same thing for how far away from the sun is it? For the Earth, it's about 93 million miles, but that's kind of awkward. So how about we just make up a new unit and call it 1. 1 AU, AU is astronomical unit, and 1 year. That makes all these calculations a lot easier because we're dividing by 1 cubed and 1 squared. Now for Jupiter, if you look at Jupiter and you wait for it to reach the same point in the sky again where it's in front of the same set of stars as it was last time, that's going to take 11.9 years of our years. Well, if you square that guy, so what we're going to do for Jupiter is 11.9 squared divided by 1 squared, and then we're going to cross multiply by 1 cubed. And that's going to get us a calculator. That gets us 141.6. And then we're going to take the cube root of that in order to get how far away from the sun is it on average. So take the cube root, and that gets us, so cube root, that gets us the average orbital radius of Jupiter is 5.21 astronomical units. So however far the Earth is on average, multiply that by 5.2, and that's how far away Jupiter is. Now, Kepler figured these guys out. He had no clue why they worked. Maybe he had an inkling, I don't know, I wasn't there, but he did the curve fit, and look at this. You're trying to find a square and a cube. No wonder it took him almost 10 years to do this. We've been doing this in class a lot more quickly because we have computers to make graphs, and then we just say to the computer, hey, apply a power fit, tell me what the exponent is supposed to be. He didn't have that. What he did have was 20 years worth of data. Now Newton comes along about 70 years later, and he helps explain why does this work, or how does this work, I should say. Physics doesn't do why very well, physics does how pretty well. So he developed his 3 laws of motion, and then he also developed his law of universal gravitation that we've already discussed. And if you put those guys together, you can end up with this. So let's look at that derivation. So if you start out with force causes a mass to accelerate, over the course of a whole orbit, you can, as long as it's close to a circle, you can pretend it's a circle. So let's pretend it's a circle. That's why I'm going to say circular motion. So gravity is what keeps the planet in orbit. So over here, we've got the gravitational attraction. And then over here, it's moving in almost a circle. Almost a circle. So let's say because it's almost a circle, let's pretend it's a circle. And the big M is the star, the sun, and the little m is Earth. So notice that the mass of the satellite doesn't matter. The mass of the satellite disappears. That's irrelevant. And as long as the mass of the sun, let's say ms, as long as the mass of the sun is significantly bigger than the mass of the satellite, then this r and this r are going to be the same. The distance between the two objects and the radius of the circle is going to be roughly the same. As soon as you have two celestial objects that are similar in size, those two r's are not going to be the same. When would that be the case? Binary star system. If you have a binary star system, then the size of the circle and the distance between them won't be the same. But for us, where we have a planet that's tiny and a star that's huge, this r and this are basically the same thing. So we've made two approximations here. One approx with circular orbit, and two, assume mass of the star much bigger than mass of the planet, such that the distance between them is the same as the, no, sorry, I got these backwards. The distance of the orbit and the distance of the circle are the same. All right, these are two assumptions that we're making in this equation here. And it works pretty well because we're going to end up back at the same place. And this is a more true equation because it actually fits the data. This is your theoretical underpinnings and the background for how we can get this and show how this works and learn a little bit more about our solar system. So let's play with this a little bit more. If we're going to go around a circle, then we have the velocity of a planet or a satellite going around something. So v equals 2 pi r over t. And again, that's going to be not the distance between them, but the size of the circle that the planet is tracing out. They might not be the same thing as soon as we have a binary star system, but for right now, we're going to say that they are the same thing. So we're going to say that these are the same. I'm going to get rid of these subscripts because I'm saying that they're the same. So GMS over r squared equals 4 pi squared r squared over t squared, and then I have another r there because I didn't cancel that out. Now let's cancel stuff and rearrange it a little bit. GMS over 4 pi squared, and that guy's going to cancel one of those guys. And what we're going to get is big G, which is constant of the universe, mass of the star divided by 4 pi squared, and those are just numbers, is going to be equal to the average, the radius, the orbital radius of the planet cubed divided by that planet or that satellite's period squared. Now, what if I go through the same exact calculation or derivation for Jupiter? So let's say that this guy is Earth. So we have radius of the Earth, speed of the Earth, radius of the Earth, and then period of the Earth, and then this guy is Earth. Let's go back and do it all over again for Jupiter, and all I'm doing is changing the subscripts on my r's and my t. So then I can end up with radius of Jupiter cubed over period of Jupiter cubed, squared. And then I can rearrange it. I can just cross multiply. So this guy and this guy trade places, and I get an r cubed over an r cubed and a t squared over t squared, which is what Kepler came up with. Now, what about that thing in the middle? That thing in the middle is a bunch of constants. G is a constant of the universe. 4 and pi squareds are also constant of the universe. They're just numbers. And then ms, that's the thing that's being orbited. So we can get the mass of the thing that's being orbited from a bunch of planetary data. What we can't get is the mass of the satellite. The mass of the satellite disappears. We can get mass of thing orbited from satellite data. And that right there, the R's and the T's, that's your satellite data. A recent AP lab question problem gives you satellite radius, satellite period, and then wants you to make a line, and then from the slope of the line, get the mass of the thing that's being orbited. So what you have to do is you have to cube the radii and make a new list, and square the periods, make a new list, and then this is your y-axis, this is your x-axis, and then this will be your slope. So what we have is r cubed equals g mass star over 4 pi squared t squared. Let y equal to r cubed. Let x equal to t squared. And then our slope will be constant universe, big G, times mass of the star that we want to find out over 4 pi squared. And from the slope, you're going to get the mass of the thing that's being orbited. All right, that's Kepler's 3 laws with Newton's law of universal gravitation in the background, supporting the theoretical reason for how does this work. And you're going to have a couple of homeworks that tie these things together.